All right, starting a new one here. Just kind of share. All right, so we're sharing. So now, we did this module exam one here. That's done. That's your exam. Now let's take a look at the next module here. As you can see, the next sequence is going to be RSA, certificate authorities, digital signatures, Pi crypto, and so on, right? So there's quite a bit that's going on there, but they're just building up. Like digital signatures will use hash values, for instance, and then we're going to use asymmetric encryption to do something called signing of these hashes and so on. So it's just going to be, a little bit more complex. But today, we're going to start with RSA. And I'm not going to do a formal definition of RSA just right now, because it does take a while. I'll simply say that RSA is just the initials of the three people that created this algorithm. I think in the late 70s somewhere, Rivas, Shamir, and Edelman, something like that. So there's three people. And for some reason, it was given their initials as a name. So what's in here is I have several files, and some slides, basically some code. This is like a complete example of RSA, like fully implemented from scratch. There's several like algorithms within the algorithm, if that makes sense. Like there's an algorithm for this and an algorithm for that. It does rely on some math, but it's very simple math. It's actually like algebra, which is what's like really amazing, right? So it's like simple algebra. You've already seen the modulus operation, right? So we did that mod, and that's actually very significant in this algorithm. So all the math we'll start covering on Tuesday. All right, and then I have probably a PDF, more slides, RSA steps, quantum and crypto. So the reason why this is in here is, we'll assume that we have a quantum computer going forward. So if we have a quantum computer, then in theory we can break RSA. That's the big. There is an algorithm called Shor's algorithm. You can look it up. I think there's a Netflix video about Shor. He's a person who invented an algorithm assuming that understanding how quantum computers would work if they exist. So then he created an algorithm for this quantum computer, and as it turns out, it can break RSA, right? But the big thing is we don't yet have an actual quantum computer. So the day that, or maybe governments secretly have one and they just haven't told anyone. That's a possibility, right? So anyway, our assumption is that they don't exist at this time. As I've stated many times, there's the fear that they will become available. So if they do, then you need to have a new class of algorithms that are quantum safe, right? So that's where the research is right now in cryptography. But we will assume that we have a quantum computer. We need to use, you can read the paper here, Keeping Secrets in a Quantum World. So I provided this nice little article. I think you'll find it fun and interesting to read. Cryptographers are preparing for new quantum computers that will break their ciphers, right? You can see this article is from 2023, so last year. This is very recent. So take a read through it, okay, definitely, so that you can start to understand the challenges coming up in cybersecurity with this. And, it might be, if you guys work in cyber in 5 years, this might be a very real headache that you'll have, right? So, updating all let's say you're a sysadmin or something, and you'll probably have to update all the cyber cryptography algorithms in your network or something like that. So it's something. But anyway, read through the article. The way that we're going to simulate the quantum computer is with Python. So Python has a lot of libraries, and we're going to bring in a library called the KissKit or something, one of those. Penny Lane is the other one. So either one of those libraries we will import. I'll show you guys how to write some code, and that basically would simulate that we have a quantum computer, and then we can just call Shor's algorithm and boom, break RSA. I'll show you mathematically how you would break RSA. You already know how to do this, actually, because it's factorization. You learned this in probably like what, elementary school or something, like factorizing numbers, right? So 2 times 3 is 6. 6 times 2 is 12. So you just got to do the reverse of that. So that's called factorization. And that's it. That's how you break RSA. All right. So you already know how to do that. So we'll get to discuss that later in the semester. But initially, we will just learn how the algorithm actually works, which, like I said, is algebra. So usually I should have a Word document in here. And raise your hand if you guys have any questions. But yeah, so I have this Word document. I usually start with this. You can see I have several problems in it. So let's just discuss it. And then I'll start implementing in Python our very first RSA. As you can see, that's it. That literally is RSA right there. Simple. That's an equation, right? M to the E mod N. Boom. The challenges are, how do we calculate, this E, this D, all that stuff. But mod is an operation. We've already done it in class, right? You remember we did that for the substitution lab, I think, or one of those where we calculated mod, if I remember correctly. All right. So again, remember Bob and Alice. So today I'm only going to introduce this one. I'm not going to even assign a homework, really. We're just going to code through this. I don't like to break homework assignments, right? So you have your homework assignment already for next week. Next week, I will finish all these 4 problems, as it does take a while to get through this lab. All right, so public key infrastructure and certificates. So that's the wide topic for this second third. Again, why do we need this? The motivation is quite simple. For the first 6 weeks of the semester, you've been hashing, encrypting things, and you sent to your classmate all these files, and you always had a problem. That key, that secret key, you were always sending in clear text, right? Plain text. So you basically, you weren't able to achieve confidentiality because somebody could intercept your email, extract that secret key, and they can decrypt everything. So the motivation is that we now need to be able to encrypt that secret key. All right. And the way that we do it is with asymmetric encryption using public and private key cryptography. So it's a topic I've kind of discussed a little bit. And so now we're going to go into it in a lot of depth, especially on how it's done and the corresponding algorithm for this, which is the RSA algorithm, or elliptic curves algorithm. I think elliptic curves are actually used in blockchain and cryptocurrency mostly. And there's also the Diffie-Hellman is a third approach that can be used as well. All right, so yeah, so let's look at the problems first, right? So this will be your first homework assignment. So we got problem 1. It's what I call a toy view of RSA. Then I have, then you're going to just change the values and try it out. And then after that, I will provide another piece of code that's loaded already on Brightspace here. And that's a more realistic implementation of RSA, a more complete one. As usual with all these, I will state again, never use this code that's written here for actual encryption, as it's not the math that's wrong, but probably the implementation of it. This may have an error somewhere in there or an insecurity. If you have those things, someone will find it and hack your stuff without a doubt. So you want to use things that have been proven, like OpenSSL, et cetera, to be more secure always. All right. Yeah, and then usually the last problem, as you can see, problem 4, using the code from problem 3 plus any symmetric encryption approach. So notice how in this problem, I'm basically just saying use everything that you learned from the past 6 weeks, but now using the code in problem 3, send a message to your partner and achieve confidentiality. This will be the first time that you can actually achieve confidentiality because you're going to exchange the key securely. So this time you must exchange the symmetric key securely, basically. Pretty easy and straightforward, right? All right, so that's problem 4. So let's read problem 1 in full. So this is basically all we're going to do today in the time that we have left. It's fine. So Bob wants to communicate with Alice. He wants to send her a message, M, which in this case will be the key, right? So remember, this is not for a movie or a big document. Bob knows the public key of Alice, which is actually n comma e. So as it turns out, public and private key is actually made up of 2 parameters. So it's a tuple of 2 things. So now Bob knows the public key of Alice, n comma e. Now Bob encrypts the message M using Alice's public key. Bob converts his message into a number M, which is what we're going to do. So just to keep this very simple, our message might be like hello, but we're going to convert it into numbers in this example. And then later on, I will show you how to actually take a message and get everything that we need. For this example, it'd just be like 62 or 42 or something. Using the number M, Bob creates a ciphertext C using the following equation. So this is actually, that is E. Remember, if we talk about an encryption algorithm, we know that it's a pair of highly efficient E and D functions, right? So in this case, the encryption function for RSA is just this one over here. That's it. But calculating these parameters is actually a little bit hard sometimes, right? So we're going to have C is the cipher, M is the plain text. This is raising something to the power of, right? So M to the E. And E is going to be called the encryption exponent in this case, which is in relation to N comma E over here, okay? So like I said, I will provide a very formal explanation of this with all the math, but for now, I'm just kind of like, we're just going to try to code this for fun so that you guys actually see that it's simple. So we take M to the E, and then we mod. Mod is the operation that we looked at already in Python, which if you remember was a percentage sign. Gives you the remainder. We'll go over that as well. And then N, right? This is a value that has to be calculated, okay? So that's, it's going to take a while. We're going to have to select 2 prime numbers. It gets into prime numbers. I don't know. You guys know what prime numbers are, obviously. So I will ask you, who wants to volunteer and tell me what prime numbers are? What's the formal definition? Yes, sir, please.
Numbers that are only divisible by itself.
Yes, exactly. And this whole thing depends on prime numbers only. So it gets really fun, right? It gets the whole, there's a lot of stuff. People over the years mathematicians have spent a lot of time studying prime numbers and trying to find patterns in prime numbers. They're very interesting because there is no pattern. It's like very odd. And they just keep going. If you Google, for instance, you'll find that at this point, someone has been able to compute up to a certain number of prime numbers. And because they have very powerful computers, but there's still some prime numbers probably that haven't ever been computed because they get so large. Do you see what I'm saying? So it's weird. And there's no real pattern, but it's a whole field. Okay. Anyway, so we'll look at that. Usually our simple examples will use prime numbers like 17 and the next prime number 53 maybe might be a prime number. So we'll look at that. So we'll need algorithms just to give us prime numbers, right? That's one of the things that we will need and so on. All right. So anyway, guys, any questions? Anything? All right, so once we have the encrypt function here, C equal M to the E mod N, then that's how we encrypt the message. So imagine here, this would be the secret key, right? So we take the secret key, boom, cipher. That's what you send when you're doing the encryption, working with your classmate, and now you have finally solved the problem of how to exchange the key securely, right? You have to use, of course, if you're sending the message to Alice, you'll have to use Alice's public key to achieve confidentiality, Remember that we can also achieve authentication by reversing the set of keys, right? So that's something else that we're going to study as that's important for certificates and things like that. All right, so let me got a little bit of it. All right, now Bob transmits the ciphertext C to Alice. Alice receives the ciphertext from Bob. Alice will use her private key to decrypt the ciphertext to get the original text, right? This is done using the equation below. So now if you look, decryption is similar equation, but the algorithm has other steps to calculate the parameters. So assuming we've already calculated D and N, then it's pretty straightforward. To get the message back, we take the C that we receive, C to the power of D mod N. Now this D, imagine this D can get really big, right? So you actually, if you try to, like calculate this on a calculator, it may not work because you might be talking about C to the 1, 3, 5, 7, 8, 9, 3, 5, a very long sequence of D. We already actually printed a public key and a private key. You should have noticed that the private key is actually longer than the public key, but they're related, right? Remember that as well. So now Bob transmits the ciphertext C to Alice. Alice receives the ciphertext C from Bob. Alice uses her private key to decrypt the ciphertext to get the original text. This is done using the equation. This one, C to the D mod N. This N here is the same N as this one over here. Okay. Now D is called the private key component. So where D is the private key of Alice, I should have said is the private key component, and E is the public key component, right? Because they're actually a pair. E comma N, D comma N. The letter N is the product of P and Q, okay? Which is very simple. That is N equal P and Q, which are two randomly and independently selected large prime numbers such that P and, not equal to Q, all right? So they're supposed to be really large prime numbers, okay? But here in this example, I'm just going to use very small numbers, of course. But as this starts to become more realistic, they should be pretty big. Okay. So now we're just going to kind of do this problem. So assuming that M is 7, P is 5, and Q is 3, and that the keys are E equal 3 and D equal 3, then we're going to calculate the value of C. Okay. So we're going to write a Python program that demonstrates this. Does that make sense? Now, notice there's something here that is not correct, right? So I'm showing you this later when we do this exercise. You're going to repeat in problem 2 the exercise in the correct way. But just notice that here I've made E equal to D. That's not correct, right? That should be very obvious. D is the private key. It should be kept secret. Got it? Make sense? All right. Key component there. P and Q, are they prime numbers? Are 5 and 3 prime numbers? Mm-hmm. Yes. Right. Okay. Perfect. All right. So we're going to do that. Write a Python program that demonstrates this. And then problem 2, using the code from problem 1, we're just going to repeat it. Encrypt M equals 65. Calculate the cipher. Assume that the public key is 17, P is 61, Q is 53, and D. Notice how quickly D gets really big, right? And just like these tiny numbers. So imagine as we start getting more realistic, this is going to be much, much bigger. Problem 2 is this problem 2 also I will do by hand. So we'll see later in the lecture on Tuesday, we'll by hand try to solve this mathematically, but it should correspond to these values and hopefully we'll get the same parameters. Got it? All right, so any questions on any of this? So we're just going to do this one first, all right, and implement it in Python. Got it? All right, so let's go ahead and go back to the virtual machine, basically. Which was on. What happened to my VM? All right. All right, I'm gonna run to the bathroom while it's doing that.
So I think you can really have to do this. Sample. We'll give you some. We want us to make we're getting nothing, so it's the one that's been this week. Don't know what I'm down. It's just because I got switch. Yeah, no, I'm saying over there, I can start scratch on the cooking machine and putting that together. The Python and such, yeah, the training there that creates space. Think about nothing but the level since it's showing it's showing cartoon. Things that don't come first. It's my boss and what is part of me. So usually they get they should be they do so like give you but some of these corridors they seem really extremely like you can't bring it anymore. Oh. This is
Let's go over here. Let's log in. So I'm going to create a new folder for this. Again, most of these scripts should be on the GitHub, so you can get them from there. Let's open up the terminal. Okay. /L. Onto the desktop. CD, yes, 350 later. All right, so MKR, RSA, CD into RSA. All right, there we are. So this is our folder. This will be the first script that we're going to do. So we'll find this. All right, so here it is. All right, so let's start. So I'm going to call this toy RSA. It's literally just, very simple, just so that we become, better acquainted with the basic logic of this. It's going to be some functions, the mod operation, etc. And then, of course, there's way more that needs to be added here. So we don't need libraries for this because we're building everything from scratch, except maybe a random function, etc. But let's create, according to this, cipher. So it's the same idea as before. We have a plane and and a cipher. So the plane will be, in this case, M equal, I think it was 7, if I remember correctly, right? M equals 7. So then we're going to create the plane cipher, sorry. So we are going to need a function, encrypt RSA. Let's call it simple. Pretty simple. All right, this function will take in what? The message, the encryption exponent, and n, which is sometimes called a modulus, by the way, which is confused. It can be confusing with a mod operation, but n is called a modulus. All right, so let's then m, comma, e for the encryption exponent, and n. Right, so these three parameters. So of course, n would be some value, okay, which is, and then we need P and Q. Let me read the problem again because I can't remember. So P is 5, Q is 3. So N should be 15 because N is P times Q, right? And then M is 7. And E and D right now are the same value just because it's simpler for me to remember, but that's actually not correct. So before we did the actual encryption and decryption, you would need to calculate E, you would need to calculate D. All these parameters would have to be calculated. We have P and Q. So that means we would also, the 2 prime numbers. So I'll just put a comment, the 2 prime numbers. Okay. So in this case, then it was P is 5. So now I can go in here, 5, and then this one is 3. Any questions, guys, so far? All right, now we calculate n, and n should be p times q, so that's simple enough. So actually, very interesting here. This is the key to factorization. That is to say, this is the key to breaking RSA. I'll tell you right now, right? So n is available. When you go to the public key of someone, someone's public key on the internet, it's going to be e comma n. So the n is right there. It's just a really large number. But if you think about it, n is equal to p times q. So it's very straightforward, given p and q, to obtain n. It is not straightforward to have from n get p and q. Do you see what I'm saying?
Wouldn't you just have to find two prime numbers that equal it?
Go do it. Go do it. Go break RSA by doing that, please.
No, I mean like the basic concept of how
The basic concept is very simple. Go do it. Go do it. I mean it. Go do it. It's a very, yeah, exactly. Very nice observation. P times Q. Seems so straightforward. I'm sure somebody had this like, yeah, I'm gonna go do it. I'm gonna go do it right now. And then, yeah. Because they're really large numbers. That's the key. So so we have two ways, like throughout the semester. So you can go right now online. We're going to use something called factordb.com. And that's usually something that I have you use on the practical exam. So on the practical exam, I'll give you an n hidden in there somewhere. You have to find that n, factorize it, which basically either means use the quantum computer, the Qiskit library in Python, or you go to factordb. And factordb may already have, for a specific n, the factorized values. So I'm not saying that some values haven't been factorized. They have. But that's why you need really large values. Do you see what I'm saying, guys? Yeah. So anyway, so keep working on this idea, and we'll talk about it. One thing I can tell you is, for instance, RSA. So this actually brings up another concept, right? We've said that the algorithms are not a secret. We rely on these algorithms to be secure because they're well designed and well made. But it's not because we keep any aspect of the algorithm secret. In fact, it is very well known. And every year, there was a conference called the RSA conference. And the whole purpose of that conference was for teams from different universities, companies, to try to break RSA. That was literally all they wanted to do. So for decades, people have been trying to break RSA, at least publicly, that is publicly known, and they have not been able to do it, unless it's very small numbers, right? So the algorithm is still intact, at least at this point. That is known that with really large numbers, it's really hard to break. Okay, got it? But read the post that I gave you on quantum and RSA, and you'll see kind of the discussion on it. All right, anyway, just remember, right there, that's the key. Because as you will learn, once you do that, then you have P and Q, and you need those values, P and Q, to calculate E and D. You see what I'm saying? So if you had P and N or something, you get Q. And then if you had P and Q, then you can go in and get E, or well, D is really what you would want. And then once you find D, you can decrypt everything. But it's not straightforward to do. All right. So anyway, this is why I do this exercise, because then you can start to see exactly how it works. So anyway, we got a P and a Q. That's the two prime numbers. We multiply them to get an N. Then, given those P and Qs, we would also calculate E and D. So in this example, I think I just hard-coded them to be 3. But in problem 2, I've given you a more realistic example, which is something that, like I said, we're going to do the word problem by hand as much as we can. Keep in mind, some values you can't even calculate with a calculator because they get really big really quickly. So we need to use something like Python. All right, so, and then the message, I believe, was 7. All right, so then we would plug in all these values in here and get the cipher. So our goal then should be to print the cipher, which I think is some, I don't know, I don't remember the result. Let's look at it. So the cipher should be, doesn't say. Okay, well, something. We'll see, I guess. We need to run this code. All right. So let's go ahead and run it. I think we have all the elements to, oh, we need to define the function. So then I'm going to add here comments. Okay. So we need to define encrypt. So the same thing as before, define encrypt RSA simple colon M comma E comma N. 1, 2, 3, 4. Actually, I'm going to do one more line. 1, 2, 3, 4. All right. So now we need to implement the function for encrypting. And that's that function in the Word document that I provided. So if you go back, we're just going to implement this equation in Python, basically. So let's go ahead. So there's various ways that you can do the exponent of. There's like functions for it. And I think the second script that I'll give you next week uses that approach. Here, I'm just going to use the 2 star symbols. So I'm going to create a variable called v, just some variable. And I'm going to do, in parentheses, the first part. So the first part is m 2 stars. That means m to the power of e. Do you guys see that? And the result of that should be mod n. That's it. That's RSA right there. Okay, so then we encrypt the value. So 1, 2, 3, 4. Return B. And remember, this would be then your secret, your secret key that you're going to be using for AES or something like that. Any questions, guys? All right, so let's try it. Let's see if it works. Control X, Y. Can I use Python 3? Okay, so that's the cipher, 13. All right, so then what would you do? You would send that 13 across the internet. And now somebody would get that 13. It can be intercepted by Zelda, whomever. When 13 arrives at the other end, you decrypt it, and now you have the secret key. And now you can use that secret key on your favorite AES, DES, whatever we've been doing for the previous 6 weeks, and now you can achieve perfect confidentiality. That's it. Obviously, this is a toy example. We need to look at the actual real algorithm. So I do RSA like in 3 ways. So we do this first, then we're going to do a from scratch pure RSA algorithm, which is it's accessible actually, but it's a lot of code. And then after that, we will just use libraries. So we will use either OpenSSL or we will use PyCryptoDome, which is the standard. And if you use like the Seed Labs book, which you might use in other classes, they use it there as well. So it's pretty well known. All right, so now let's do this decryption part. So I'm going to go ahead and go back to my toy RSA. And now what I would do is I would decrypt, right? So now I get new plane. I'm going to say decrypt RSA, simple, so simple is basically a toy. And then here, what would I provide to it? I would provide C, which is the cipher, which is actually cipher, right? I need to provide the cipher. I also need to provide D, which is the decryption exponent. That's the private key right there with N. So literally, these two parameters here are the public key. And these two parameters here are the private. Okay. And when you're Bob and you create a public and a private key, you are literally creating a pair of these. This is what you will make available. Others. That's it. All right. All right. So this should give us new plane. And then we're just going to go ahead and print new plane. Okay, new plane. Now we need to define this function, of course. So it's going to define decrypt RSA, simple, colon. All right, so this takes C, cipher, D, decryption exponent, and N, the modulus. It's called 1, 2, 3, 4. All right, so now let's do the decryption part. You can use another letter, let's say K. Well, actually, that make you think of a key. Let's do T. All right, T. And again, I'm going to use parentheses here. I'm going to take C. Okay, so what am I going to write here? I'm going to write the equation for decryption. So this was the equation for encryption. This is the equation for decryption of RSA. Okay. Let's go ahead and do that. So it's going to be C double asterisk. Oops. Double asterisk. Yep. And D. And then the result of that mod, which is the percentage. That's it. All right. And then now, 1, 2, 3, 4, return T. And we just return the decrypted value, which should give us 7, which was the M that we provided. So that should do it. Any questions, guys? Control X, Y, enter. 7 right there. That's it. In its simplest form that I can think of, this is the RSA algorithm. All right, so for the rest of the next couple of weeks, we'll spend some time looking at this algorithm. And, you know, there's several functions that need to be used. So for instance, to get D, we actually have to take some parameters, and it's in an iterative way that we need to find that D, for instance. Right, so there's an algorithm for that. So like I said, RSA is actually a combination of several algorithms that are needed to be able to find specific parameters. Most of the math is algebra. Okay. All right. So we've done this one, problem 2. Are there any questions on problem 2? Or sorry, problem 1. Questions? All right. So I think we have like 8 minutes. So we have just enough time to do problem 2, or what will be your homework due 2 weeks from today. So let's go back to the Word document in Brightspace. All right. So we did our toy example. Okay. Here. Now let's look at problem number 2. So using the code from problem 1, encrypt, but now we're going to use new parameters. Let me write these down. Okay. So it says here that we need encrypt. The message is 65 M. Right? You guys are seeing, yeah. M is 65. Calculate the cipher. So we want to calculate that. Assume that the public key is public key exponent, I should say, is, or E, sorry, no, E is 17. The prime numbers, P and Q. So P is 61. Q is 53. And you should check to make sure those are prime numbers. They should be, but okay. And notice that D is a much larger number in comparison to those. It's 2753. Okay. All right, so let's go ahead and repeat the exercise with these parameters. That's all you would have to do in this lab. So plug in new values, basically. All right, so I'm gonna use the same code. All right, so it says here that P is 61. 61. Q is 53. All right. Then I'm going to calculate P times Q is going to give me N, whatever that is. And then obviously we're still missing a lot of functions and code to be able to compute E and D. All right. But for now, to keep things simple, I'm giving you those values. So they would be 17 and D is 2753. Sometimes I may give you the public key like this. I may just say pub. And I'm going to say what? 17, comma, N. Or in this case, P. Well, and I have N. N. And then the private. Two, 753, comma, N. Do you see that? So I may give you the keys like this sometimes. I may put a little text file and I'll just provide them like this. So, just be aware of that. All right. So we have E17, D2753, P and Q 61 and 53. So we just need M, which will be 65. Okay. So these are the parameters. And so we want to encrypt and decrypt. So the cipher is cipher. And then we're going to say the plain text is okay. All right, so let's run this and see if it works. So Control X, Y, clear. So the cipher is 2790. Right? And then we got back that the plain text is 65, which is correct. Got it? Notice this time E and D were not the same number, right? As I had in my first example. So this is more of a realistic problem, and this is one of the problems we'll do it by hand also, and you can correlate. There's one part in there I'm not going to make you, for instance, calculate D by hand. That would be a little crazy. So instead, you can just use this whenever you have to what I'm trying to say is sometimes I may have to just give you D because it just takes too long to calculate something. Okay? Make sense? Guys, any questions? That's basically it for today. Yeah. Oh, yeah. So that's basically it for today. Just a really quick intro to RSA. I think it's like an amazing algorithm. Honestly, it's like think about everything that you do during the day, and it's thanks to it, right? Without this, you wouldn't be able to do banking. You wouldn't be able to go in Brightspace. You wouldn't be able to have Netflix. So many things, right? So power of math. Right. All right. So anyway, so we've gone over it. We've done 2 examples of it, problem 1 and 2. Next week, on Tuesday, I'll give you the lecture, obviously. So formally, we'll discuss go deeper into the math of it. And then we'll do problem 3 and 4, which are actually a different script, right? So that is going to be the actual from scratch RSA code, and it's a full implementation of RSA. All right, guys. So I'll stop the video here for today. And then